So I'm Ahmed Zerouali, and I'm actually a postdoc at the University of VUB in Brussels. And I'm also a fellow researcher in the SecoAssist project, which is a research project that studies software ecosystems of the future. And today's presentation is going to be about a measure or a measurement, a metric that we have came with, which is technical lag, and how we can use it to quantify the outdatedness of packages and dependencies. So as you know, there are now many and several package managers, and in this package manager we can find thousands of libraries and sometimes millions of versions of these libraries. So while it is true that this huge availability of packages and libraries, it's good, and it facilitates development, and it helps, it improves software development in general and its evolution, it can also cause problems. Why it can also cause problems? Because packages, they have several versions, so they are always creating new versions, and it's a bit hard to keep up with creating different versions and updates always to the new versions of the dependencies. So for this reason, it's a bit difficult to know when to update and when not to update. So we know that if we have some dependencies that are outdated, so this means that we are missing some functionalities, missing bug fixes, vulnerability fixes, etc. But should we update to have these functionalities that we are missing? Probably we are going to face backward compatible changes. So in the same time, so we have this fear of backward compatible changes and the effort to update. So there is this balance between do we want to update, and if we want to update, can we do that or not? So to study this delicate balance between updating and not updating, we have came up with this measure, the technical lag metric, which is actually the difference between a version of a deployed software and an ideal version. And the ideal version here, it can mean different things. So the ideal actually depends on our gold standard. So now we can say that in most of the tools that we can see, the ideal is the latest available version, but there are many cases where when we are deploying a software, we don't want the latest available version, but we want the most stable one, or we want the most secure one. So depending on our gold standard or on our view of the ideal version, we can say that we are being outdated, we are missing something or not. And then to compute the difference between the ideal version and then the deployed version of a software, we can also use different measurements. So we can use the bugs that have been fixed in between, the vulnerabilities that have been fixed. We can just compute the number of versions in between, the lines of code that have changed, functionalities added, etc. So if we look, for instance, at the Debian project, so in Debian we have three snapshots or three distributions. We have testing, we have the stable version, the old stable, and the testing. So for users that care about stability, they can use Debian stable, and in this case they will get functionalities that have been verified and checked many times. And if they care about functionality, so in this case they should use testing. And if they use testing, yes, they get the latest functionality, but maybe they will also get some bugs that are still not discovered yet. And for those who care about security, they can rely on those distributions that are stable, but also benefiting from security support. So if we take this example here to know exactly how the technical lag can occur. So if we consider that we have a package P, a dependent package P that relies on a dependency D, and then the latest version 4.00 of the dependence relies on the dependency D using a constraint caret 1.0.0. So in this case, we see that the latest version is actually being up to date. But if after some time the dependency released new versions, and maybe in this case are major versions, and also the dependent released a new version but didn't change the constraint, in this case we will find that the dependent is using a dependency that is being outdated and is missing some updates. And actually, it has been shown that these constraints are one of the main reasons of why packages are or dependencies are being out of date, are used while being out of date. And if we look, for instance, I mean, there are different package managers that have different constraints to allow a range of versions to be installed. But if we look at NPM as an example, we can find that it has two popular constraints, the caret and the tilde. So the caret means that all new patches and minors are allowed to be installed, and the tilde only accepts patches to be installed. And also there are other constraints, of course, like the star, which means that all versions that are available, they are allowed to be installed. So while it's really important to study the outdatedness of one individual package or the technical lag of one individual package, it becomes actually even more important when we want to study the outdatedness in a huge ecosystem, in a huge dependency network, in which we can find packages, they rely on each other, and there is a lot of movement. And especially in ecosystems where we can find dependency constraints. And so to take all these variants into consideration, we had to actually formalize, or we had to create a formal framework for the technical lag that can capture all these variants. So the ideal could be different, the ideal version could be different, the difference between the ideal and the deployed software version also could be different depending on what we want. And also, I mean, usually we don't only deploy one software. I mean, we don't only rely on one software package or library, but we rely on a set of dependencies. So actually, we should not just compute the technical lag for one deployed library or for one used library, but we should compute it for a set of used libraries. So we should find a way to aggregate the results over a set of used dependencies. And indeed, so we created this formal framework of the technical lag as a tuple of a set of component releases, a set of possible lag values, and the function ideal that returns the ideal version of a used version, and then the delta, which computes the difference between two component releases, and an aggregation function that aggregates over a set of lags. And then we had to include other functions. So the technical lag function, which returns the difference, the delta between the used version and the ideal one, and then the aggregated, the aglag, which is a function that returns the aggregation over a set of lags. And after that, so the creation of this formal framework, we actually wanted to show the applicability of the framework. So we applied it to two case studies, NPM and then Docker. So more specifically, we studied the whole registry of NPM packages. For all NPM packages, we checked their dependencies and then the transitive dependencies, resolving the dependency constraints, and then finding the correct versions that are installed, and comparing them with an ideal version. The ideal here, we consider that it's the latest available version. And also we did the same with Docker images. So we considered for all Docker images that are based on Debian that exist in Docker Hub. So we pulled them and ran them locally, and then extracted the Debian libraries that are installed in them, and then we compared them to the latest available versions in each distribution. So to instantiate the framework, we considered mini instantiation actually, but I'm going to talk only about the time-based instantiation and the version-based instantiation. So for the time-based, we consider the ideal is the highest available version, and the delta is the difference between the release date of the ideal one and the used one. And as an aggregation function, we use the max. And also for the version-based instantiation, so we consider the ideal is the highest available version, and the delta is actually the number of all updates. It's the sum of all updates, but grouped by type. So the number of all major versions, all minor versions, and all patch versions. And as an aggregation function, we use the sum. So if we take this example here, if we consider that we are relying on some dependency, and we have a lag, technical lag between the versions 1.10 and 2.01. The time lag would be just the release date between difference between the release date of 2.01 and the release date of 1.10. And for the version lag, so we check what change happened from 1.10 to 1.20. In this case, it's a minor change. So we say we have one minor, and then we have a major change. And again, one patch. So we say that the version lag is one major, one minor, and one patch. So studying this for the whole ecosystem and for both runtime, for the whole ecosystem of NPM and for both runtime and development dependencies, we found that actually the version lag is increasing over time, in the sense that packages that have been created recently, they have more outdated dependencies at their release time than packages that have been created in the past years. We have also noticed that actually the dependency constraints are the main reason behind this outdatedness in the ecosystem, and we found a small difference between development and runtime dependencies, in the sense that development dependencies, they have more outdated and more technical lag than the runtime dependencies. And actually, we noticed that the increase in the major version lag actually coincides precisely with the time when the caret was introduced in the NPM package manager. And after that, we studied the time lag, so always just for direct dependencies, and we found that the time lag actually was increasing until 2015 and started stabilizing. So we can see a difference between the time lag and the version lag. The version lag is increasing while the time lag is stabilizing. This means that the recent packages, they are updating more than before. That's why we have more version lag, but the time lag is actually stable. And then we studied transitive dependencies, and we found that the technical lag is accumulated from a level to another level in the dependency tree, in the sense that dependencies that exist deep in the dependency tree, they have a higher technical lag. They are more outdated than the other dependencies. We also compared between packages and applications that are not distributed via the package manager. So they exist in GitHub, but they use NPM packages, and we found that these applications, they have a higher technical lag than packages. That's probably because they are not really intended to be used, while the packages of NPM, they are intended to be used by others. And then for the second case study, so we studied Docker images and the Debian libraries that are installed in Docker images, and we found that in most of the cases, the majority of libraries are actually up to date. And for those who are out of date, they are just outdated of one version. So the version lag is one version. But we noticed that actually this outdatedness is related to the type of the Debian distribution that is being used. For instance, here you can see that we have a higher version lag for the images that use old stable and that use testing, but not for those that use stable. And that's because we found that old stable was not updated in a long time, while testing, in testing we can always find new versions, so it's really really difficult to keep up with the updating process of packages that are released in testing. We also combined different dimensions, different measures of the technical lag. So we associated the technical lag for the time, versions, the number of vulnerabilities, bugs, and we always found something different. So we found that all the dimensions that we considered are actually complementary. So as a conclusion, I think that we think actually that the technical lag is a good measure to quantify how outdated dependency is, or a deployed software in general is, or a set of deployed software. And we think actually it would be a good idea to include it in tools like Dependabot or Renovate or other tools that check the outdatedness. So before saying you are outdated and you have to update, first say, okay, you are outdated, but you are outdated with this number of versions. You are missing this number of API breaking changes. So really give something that the developers can compare, can decide whether they want to update or not. Yeah, and that's it. Thank you.
Okay, thanks a lot. That was really interesting. Let me see if we have any questions. So there was a question in the chat. What are the resources required to pull all images based on Debian on Docker Hub and run them locally? What did you use to do that?
Yeah, so we actually just first relied on the registry to identify the registry of Docker Hub, to identify the library, the Docker images that rely on Debian. So we first identify them by looking at the signatures of the layers, etc. And then when we identified all layers, all images, we actually just did a brute force. We just started pulling them and running them in parallel. So it took us about 1 month to study about 900,000 Debian images.
That's ridiculous. What did you use to find the images that were Debian based?
So to do that, actually in Debian we have a mechanism that sorry, in Docker you have a mechanism that you can rely on another image, and when you rely on another image, you inherit all layers that are in that image. So we actually took all images that are coming from the official Debian repository, and then we compared their layers to all the other images that exist in Docker Hub. So if we find that the set consecutive set ordered set of layers are actually exist in another image, then we say, okay, this image is based on the other official Debian image. And actually, we found that all images that we identified were indeed Debian images.
Okay, so you did that manually.
What do you mean by manually?
you had to go and look at the images and download them, do Docker inspect and find. Yeah.
Yeah, but it was automatic. I mean, we did just create a script and then leave it for
Yeah.
1 month.
Okay. 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 There's a question about slide 25. What happened since 2017 where we start to observe a big and increasing difference for the green curve?
Actually, that's a good observation that we also had, but we didn't find I mean a reason for it. So the data is actually used by is coming from libraries.io. We contacted libraries.io and they said that there is no problem with the data, but we couldn't actually find out exactly why we have this increase. Of course, we found that it's related to the use of the constraints. So more strict constraints are the GitHub applications are using more strict constraints, but why? Since 2017, we don't know why.
Oh, whoops. Yeah, so multiple patch versions can be released for the same fix. Example, 1.1.1 can move to 1.1.2. 1.2.1 can move to 1.2.2. Was this taken into account?
No, actually, we just relied on the semantic versioning. So we just relied on all versions that we have. We ordered them by number and not by date, because we can have backports. So we ordered them by number, and then we just find the difference. So it's a simple measurement, but it shows that there is potential actually there to give more insight about how outdated our dependencies are.
So I have a noob question. Where do you get that ideal version
So
to
the
measure the
ideal,
technical?
yeah, the ideal version depends on what we want. So actually, we did some interviews with with developers and with maintainers of some big companies, and we noticed that the ideal is different. I mean, it's always on. I mean, it's the maintainer. Sometimes we can find that the ideal is the most secure version. Some other developers said that they want the most stable one. So some wanted the ideal to be the most documented one, the most tested one. So I mean, the ideal depends on the developer. We can't say that always that this is the ideal. But I think for now we can say that most of the tools consider that the ideal is the latest available version or the highest available version.
Okay, so if basically the takeaway from that is if you're not at the latest and greatest version for all of your dependencies, then you are experiencing technical lag. Yeah.
Yeah, in the study that we did, but it's not always the same. It depends on the ideal. I mean, if our ideal is the latest, then this study shows that the technical lag is high and it's increasing over time, etc. But if the ideal was different, like considering, as I said, the most secure one, the version with the least number of vulnerabilities, maybe we would have found different results.